Hi, this is Professor Cummings, and I wanted to do a video on the integrating factor itself. Particularly, I want to just prove out the integrating factor. A lot of people, we discussed the integrating factor in other videos, but I wanted to make sure that, I guess for some people it doesn't sit well, that they don't know where it came from. They've got this equation that they're expected to use. And I just wanted to show how it functions and how to be able to know you can trust it. Trust it for what it is. So here we go. Let's go ahead and explain this integrating factor. What we have, again, if you remember what the definition or what the reason for the integrating factor was in the first place. It was basically to make a first order linear differential equation problem, something that you could actually integrate in order to solve it, for y. And in order to do that, what we were doing was multiplying through the entire equation in standard form by the integrating factor, which we're representing as u of x. Right? Now, u of x times p of x has to be a derivative of u of x itself, the integrating factor itself, in order to put that first order linear differential equation in standard form into the form of the product rule, which makes it much easier to integrate. So this is what we're trying to get to where u of x times p of x is a derivative. So if we start from that point there, we could multiply both sides, divide both sides by the integrating factor. So the derivative of u of x divided by u of x actually has a function that's just the part of the product or part of the conditions of derivatives, comes out to being the derivative of the natural log of the integrating factor. Right? That's just the property of derivatives. Right? Now, if we take this and we're trying to solve this for u of x, trying to put everything in terms of u of x, what we can do to get rid of that derivative on the right side of the equation is to integrate both sides. Right? The integral of p of x is equal to the integral of the derivative of natural log of u of x with respect to d of x. So we integrate both sides of that equation. And now we want, on the left side, we're going to kind of leave that alone for now. On the right side, the integrating factor, that infinite sum, and that derivative are going to cancel each other, leaving us with the integral of p of x is equal to the natural log of x. Now I'm going to crunch myself for space. So the natural log of x. Now, if we want to get rid of this natural log, again, we're trying to get it into terms of u of x, we raise everything to base e. E to the integral of p of x d of x is equal to e raised to the natural log of u of x. The natural log and base e cancel each other, and you're left with u of x. And this is where we get the whole, the integrating factor u of x is equal to e raised to the integral of p of x d of x. So that is how we get that. And it's also one of the reasons that, it was able to get this. So we can actually do that integration so easily, because it actually brought us back to this was what we actually needed, that relationship to be true. So this is Professor Cummings. And again, if you have any questions, any comments, or, go ahead and leave them in the comment section. If you have, like the video, and as well as if you want to share this video with people who may actually need it, to help them out in their classes, I'd appreciate it. Again, thanks for watching.